We'll be starting our presentation.
Welcome everybody. My name is John Moreland. I'm the program manager here at DOT.
And my name is Amrit Kunaradne. I am the deputy program manager here at DOT.
So first off, thanks for coming. We're really excited to give you today's presentation. We usually start with an introduction from our panel. So I guess we'll just start in this corner and kind of work our way around. Just let us know your name, where you're from, and interesting.
Chris Brown, interesting background in the principal here.
I'm Ryan Stahl. I'm an engineer at Raytheon. That's interesting. Hi, I'm Steve Kaufman from Boeing, guidance, navigation, and control engineer, and I have two cats that are rascals.
Hi, I'm Nolan. I'm a recent graduate from UC Berkeley. Currently unemployed, but that's because I'm going to graduate school.
I'm Gurmohan Devri, and I teach here at the Cal State Physics Department.
I'm Kevin Maston. I work for Northrop Grumman. I'm a project manager for construction there.
I'm George Kirkman. I started a company called Rolling Robots that teaches engineering and technology to kids. Prior to that, I was an engineer at Boeing in space.
Janet Lewis, I teach AP Calculus.
Kim Sung, I work for City of Los Angeles Public Works Department, Bureau Engineering. And I'm Puk Lee, I'm a civil engineer, and I work for City of Los Angeles.
Okay, so we start back up there.
Susan Carlay, I teach English and AP Psych here, and I'm the small community lead teacher.
Both for Boeing Engineering, used to be mentor, summer intern, mentor for Dominic last summer.
I'm Wendy Poffenberg. I'm the assistant principal here at Kansas.
Frances Friend. I am the parent of John Moreland, and office manager at Gordina Elementary School.
Nice to see you. Yeah, responsible for these. Okay, so again, thank you for coming. So, Mr. Carpenter likes to give us a realistic engineering experience. So throughout the year, we have a few checkpoints. So today is our proof of concept demonstration. It's the second of 5 critical design reviews we have throughout the year. So today is supposed to be dedicated towards showing off all of the testing and any design updates we've had since the last presentation. However, we're also going to take the opportunity to give a run through of everything else we've done in the past few months.
So we've done tests and we made various design changes, but we've also participated in many STEM competitions and we're even interviewed by USA Today. In addition, we have added a new division to our company that lives up to our motto, Design to Inspire.
So we recognize that not all of you were here for our first presentation, so before we jump into that, we'll give an overview of that initial proposal.
So first things first, we must reintroduce ourselves as a company. So instead of giving you the same speech we had last presentation, we decided to make a short video.
Whether you're designing a product or writing a sentence, you can capture attention, spark interest. But when excellence is your standard, it takes time, focus. A well-crafted product demands countless hours and endless adjustments. Square one becomes all too familiar, and only after every rough edge has been polished, perfected, do you sign your work with a dot.
So that's just a short little preview of our documentary film that we'll be presenting at the IDP trade show in late May. I hope you all can meet. So that's just about us. Here at DOT, we're minimalists, we're perfectionists, and we came into this class wanting to set high standards for future EDD teams.
I would now like to bring up some members from our team to summarize our last presentation. Thank you.
Hi, my name is Isaiah Stanley, and I'm the Chief Scientist here at DOT.
Hi,
My name is Dominic Herrings, and I am the systems engineer. Several volcanoes around the world have the potential to destroy their surrounding towns with a single eruption. For example, Mount Vesuvius, which is 9 kilometers east of Naples, Italy, is the most densely populated volcanic region in the entire world. A single eruption could wipe out its surrounding population of over 4 million people.
Titled Project Thunderbird, the CARPE initiative has challenged out with designing and fabricating a dual-stage robotic device capable of entering through a volcano side vent, collecting empirical data while inside the volcano, and then safely exiting through the volcano's caldera with all the data collected during the mission. A vehicle such as this can be used to safely take scientific measurements and has the potential to save countless lives.
So our solutions to this challenge are Houston and Eagle. Houston will first autonomously navigate to the side of the volcano where the rotary excavation unit will drill its way inside. Once inside, the environmental evaluation system will begin collecting data and locating the target sample. Once it reaches the target sample, the specialized data retrieval unit will collect additional data. Once the internal data monitoring system senses that the temperature levels are too high for Houston's internal systems, it will initiate the Crisis Aversion Release Protocol, or CARP for short. CARP will then allow Eagle to escape through the caldera, either autonomously or using driver control, allowing it to safely transmit data back to the control station.
Following our first critical design review, we received a lot of great feedback. After our presentation, we went back to the drawing board. We completely redesigned the specialized data retrieval unit into a more effective and efficient design. We also made changes to Houston's protective casing and included an entirely new subsystem into our design.
Now, please welcome some of our fellow engineers who would like to speak of some of the tests we have performed to evaluate our subsystems.
Good afternoon, my name is Devontae Torres.
And hello, I'm Carlos Torres.
And we are the design team here at DOT. So, at our initial presentation, we had the idea of constructing a combination shell made of carbon fiber and silicone, which we believe would be very both shock resistant and sturdy.
After looking further into carbon fiber, we realized we underestimated the manufacturing process. It's really time consuming, expensive, and there's little room for error. So we decided to reevaluate our material choices without abandoning dual action performance. We have decided to using annealed steel, fire block sealant, and ceramic insulation. While the fire block sealant isn't exactly aesthetically pleasing, it is a nice protective layer that shields the annealed steel from impacts and scrapes.
While testing, we also found that these materials work very well in high temperature conditions. We tested them using a high temperature butane torch, and they performed flawlessly. Out of the 6 different materials that we tested, only the ceramic insulation, fire block sealant, and annealed steel were able to withstand temperatures over 800 degrees Fahrenheit. And the ceramic insulation itself withstood temperatures above 1,000 degrees Fahrenheit. The results were beyond our expectations. None of the materials that we chose ignited, and they all seemed like likely candidates for the shell individually. However, we concluded that a combination of both the fire block sealant and the ceramic insulation backed by a annealed steel structural support would make a very durable and heat-resistant shell.
Now we will be introducing mechanical.
Hello, my name is William Argus.
And I'm Aaron Galea.
And we are the mechanical team. The rotary excavation unit is a crucial component if Houston is to complete its mission successfully. We've made a few changes since our initial proposal, like using a perforated steel sheet to manufacture the outer cone rather than cutting it ourselves, and redesigning the REU mount. Most of these changes serve to cut down costs associated with manufacturing.
For these tests, we made a prototype that is 40% of the final size. This allowed us to make a low-cost mock-up that still demonstrated the final drill design.
We ran 2 main tests on the REU, cutting at different angles and cutting into different materials. We would now like to give you a demonstration so that you can see this for yourself.
In our initial proposal, we envisioned a simple cooling system that would extend Houston's operation time inside the volcano. This system consists of 4 main parts: the reservoir, the pump, the tubing, and the water block. Our proposed coolant is made of 2 parts: 50% distilled water, 50% ethylene glycol, also known as antifreeze.
We tested both the freezing and boiling points of our custom coolant. Our mixture is so effective that even at 15 degrees Fahrenheit, it did not freeze. On the other end of the spectrum, it boiled at around 220 degrees Fahrenheit.
We'll now demonstrate the system. Although it may be hard to hear, coolant is flowing throughout the system. Another benefit using antifreeze is that it doesn't cause corrosion. Additives in the antifreeze prevent any corrosion to the metal fittings used throughout the system. We had this set up for about a month now, and it doesn't show any signs of wear or corrosion. These tests need to be performed in order to show how the system might react in different environments.
We would now like to call up our programming team.
Hi, I'm Dietrich Henson,
I'm Laura Jackson.
and we are the software engineering team here at SAS. In our initial proposal, we divided our sensors into 2 main systems: the external evaluation system and the internal data management system. Over the past few months, we've been focusing on the external evaluation system, namely room mapping and empirical data collection.
For room mapping, we made the switch to an XT-Ion Pro camera, which is a cheaper alternative to the Xbox Kinect sensor. The camera not only records the color, but also the depth of each pixel, which allows us to convert the recording of a room or location into a 3-dimensional image. If you would like to see the finished model, you're welcome to view it at the end of the presentation.
You might have noticed that this display has been updating us continually on the temperature and humidity of the room. This proves that we have confidence that we can collect this data during our mission.
We also incorporated a vibration sensor, which, when deformed, allows us to receive notification that the robot has been struck or bombarded. So as you can see, when my partner strikes the vibration, the piezoelectric sensor, the voltage is translated to a spike on this graph.
Now, before we get technical, I'd like to answer a question that I know is on most of your minds. Why is it pink? Sadly, that's the only color that Home Depot offers. We decided to manufacture Eagle out of foam because it's very easy to machine, expediting our process. When we want to make a new iteration of our design, we simply update the CAD, put the part into the machine, and we can have a new part by the end of the class period. Although foam is a good option for making prototypes, it is not our final design. We intend to use Dibond for our final design. Dibond is essentially a piece of plastic sandwiched between 2 thin sheets of aluminum. Dibond can be as strong as aluminum and as lightweight as a plastic. We've gone through many iterations of Eagle throughout this proof of concept process. As you can see, Eagle's new fuselage is made up of 3 parts: the battery bay, the ballast weight compartment, and the compartment for the electronics. In addition, I'll be passing around the original wing design and an updated wing design. As you can see as they are passed around, one is much thinner and was machined on the mill. The other was machined on the CNC router and is thicker. This provides a much faster process for machining the wings, and it's also much more durable.
In order to create our own unique code for the final drone, we decided to look towards multi-weave for inspiration. Now, multi-weave is a strong open source software project with tons of community support. We use this software to test our flight capability and to ensure that our servos and sensors were all functioning properly. We chose multi-weave due to its flexibility, ease of access, and strong community. Now, to detect the orientation of the drone, multi-weave uses a direction cosine matrix. Using the gyroscope and accelerometer as the main sources of orientation, the software integrates the linear kinematic equation that relates the change in rate of the drone's position to the rotational rate and current drone position. Basically, it does a bunch of cool math to figure out where it's at. Using that orientation information, we can then use PID loops, or proportional integral derivative loops, to stabilize the drone. These loops calculate error and then minimize it. So as they will now demonstrate, you will cause error by rotating the drone around its available axes, and the servos will react to its movement. Multi-weave is a valuable tool for us to create a tailor-made code for drones. Now I would like to present our manufacturing team.
Hello, my name is Ricardo Perez.
My name is Ruben Rea, and we are the manufacturing team here at DOT. As you all know, with any revolutionary project, the opportunity for groundbreaking innovation comes with an equally high chance of failure. So, in our early stages of reiterating EAGLE, our risk management team suggested that we create a backup for fetching the data. So we created a new subsystem, the backup for fetching data, or BFD for short. With this new subsystem, we do not aim to replace our beloved EAGLE, but if the situation calls for it, Houston's modular design will make this a simple substitute.
EAGLE is responsible for the last leg of the mission. By this stage, all we need to do is exit the volcano and transmit the data. So we designed a two-part system comprised of a launcher and a data transmission unit. Essentially, this is a slingshot system paired with an indestructible ball.
Although this is a two-part system, we decided to prototype the data transmission unit first because it would undergo the most stress throughout the mission. So here we have a cross-section of a large-scale version we plan to implement. So the electronics for this subsystem consist of an Arduino and two shields, one for communication, which is the XP shield, and the other for power, the LiPo shield. Although these electronics are rather bulky in size, they interface very well with each other, making them ideal for prototyping. For our final product, however, we plan to design and manufacture our custom circuit boards in order to reduce both size and weight of the overall subsystem.
The data transmission module's exterior is made up of a firewood shell coated with fireblock sealant, the gray area. The electronics are cushioned with the same ceramic foam insulation we are using for Houston's outer shell. This provides both heat protection and impact resistance. These were the two main areas we decided to focus on for our test. We performed another heat test with the torch, and even after 5 minutes, under direct flame, an Arduino would still be 100 degrees within its operating temperature. We performed a drop test as well. We performed a simple middle school egg drop test. As expected, the egg survived the 10-foot drop completely unharmed. Although we aim to not replace EAGLE, the backup for fetching data is merely a precaution in case anything happens to go wrong.
My name is Brian Laren, and we are the electrical team here at DOT.
So based on our feedback from our last presentation, we made a few enhancements to our Houston's electrical system, and we streamlined our power distribution board, we adjusted our battery system, and we also upgraded our schematics and also updated upgraded our loops. So our Houston's electrical system will be regulated through our power distribution board, and for the past month, we changed and revised our original design to be 1/4 of the size and yet perform in a similar manner.
And since our last presentation, we focused more on the motor controllers for our robot. And motor controllers basically do what their name states. They can make a motor run, stop, or even go in reverse. And although they have a simple task, making custom units of the motor controller can be very complicated. So therefore, we have decided to purchase off-the-shelf motor shields, which work just like motor controllers, and they can work with multiple motors simultaneously and interface seamlessly with our Arduino. Overall, these motor shields will give us more time to work on Houston's other aspects and give us a decrease of potential for error.
So we decided to isolate our locomotion system and also our rotary excavation unit. In doing so, these two systems will be functioning with separate batteries, and by partitioning these two systems, we'll be able to will prevent them from interfering with each other.
And from our initial research, we originally purchased looms that were similar to those used by automobiles because we thought they would have sufficient heat resistance. However, we found that the polyethylene looms that we bought were very easy to melt. And since then, we have decided to purchase fiberglass braided sleeves, which can withstand temperatures of up to 1200 degrees Fahrenheit. And we also performed a torch test on these looms to make sure that they live up to those standards. And ultimately, these looms are more compact and are more than capable of withstanding the temperatures that they'll be exposed to. And with that, I'd like to introduce our risk management team.
Hi, my name is Mike Mancon, and I'm the Risk Management Officer here at DOT.
Hi, my name is James Rasmussen, and I am the Test Engineer here at DOT. As with any project, there are certain risks involved with its planning, execution, and delivery. The identification of each and every one of these risks allows us to make preparations to avoid them. With the task of designing a volcano exploring while drilling a robot, there are bound to be high temperatures, devastating landslides, and rocky terrain. Our team faces not a simple mountain of risks, we face an entire volcano of risks.
While working with the team, I've come to understand that a vital part of risk management is clear and tactful communication. Simply put, yelling and screaming at people doesn't always work. However, throughout the year, asking questions to understand the development of what has been enough, but that has led me to be able to create a compilation of risks that total over 50 identified risks.
Of these risks, one of the most problematic is that of our parts arriving late. Fortunately, we designed our own custom purchase order forms to help reduce costs and minimize shipping times.
Another risk is high temperatures, or in our case, fire. While testing the components of our robot, we utilized both controlled flames and heat guns at temperatures simulating the volcanic mercury, which average around 500 degrees Fahrenheit.
With such high temperatures, our team was sure to use safety glasses and goggles to prevent any burns. Team safety is the #1 priority here at DOT.
In the end, it all comes down to what the team wants out of our project. We could design and fabricate a mediocre robot, or we could evaluate every possible angle, and in order to mitigate every risk, to create a robot that is simply perfected.
And with that, I would like to welcome up our financial team.
I'm Tristan Malari.
I'm Sandra Lee. I'm Frances Yuan. And we are the financial team. So with our company's heavy focus on innovation, we anticipated that proof of concept would be our costliest critical design review. Our bill of materials running total is $2,800. This number includes not only stock materials and other robot parts, but also equipment necessary to perform the tests of our choice. It is our mission to independently solicit sponsors from within the community. We have received monetary donations from Sonova, Home Depot, Trans PTSO, and Kiwanis. In addition to our own private fundraising, we have earned about $2,600 up to date.
Raising funds is one of the most difficult challenges of this project. But the companies that invest in us see the value in our work and our potential to become engineers and innovators. DOT. Designed to inspire. And we want to live up to our name. We knew from the very beginning we would do more than just create amazing products. We value the fact that EDD is so much more than just the design of the robot, but also the development of a person. We want to inspire younger students to become entrepreneurs and innovators as the future of the world. The first of any EDD team, paving the way for future CARPA teams, we have started our own DOT outreach program.
By visiting local youth groups and schools, we want to encourage younger elementary, middle school, and high school students to pursue a STEM education and share our interests and passions in the fields. It is part of our mission to provide an inspirational spark for future generations. So we had a project launch at a Gardena youth group of about 30 students ranging from elementary school to high school. There, we presented our progress on Project Thunderbird, introducing the mission and our solution.
At this point in our event, we showcased the technologies we've been using in the classroom, like 3D room mapping and Houston sensor testing. Then we continue with a traditional carpet practice, a quality function deployment on alternative uses for Cheerios. And we see that students are interested, excited, and have so many great ideas.
Then, we close our event with a hands-on project, designing and building bridges and air-powered vehicles using recycled materials.
The project allows us to undergo the engineering design process with the students by identifying the problem, brainstorming solutions, and refining solutions.
Since our first event was so successful, and we know there are still more students out there to be inspired, we have scheduled 3 more outreach events for this month, and we are still in contact with several other schools and youth groups.
We want outreach to become a part of the EDD culture. We want to serve the community not only as DOT, the engineering company, but as DOT, the revolutionary company. Truly, in every way, designed to inspire.
Thank you, Tristan. That was very well said. That's all we have for you today, so now's a great time to bring up the rest of the team and start our Q&A session.
Thank you very much.